Alright guys, today we're doing section 5. Section 5 of chapter 9 is a little bit different than the rest of the chapter. So the rest of the chapter, there have primarily been 3 big types of questions. We've had ones where we're asked to solve a proof or verify a proof. We've had questions where we're asked to verify a rewrite using trigonometric properties from different pieces. And ones we were asked to use a triangle that was given or a ratio that was given to solve for a new ratio. Now, each of these primarily use the different trig identities we talked about in class. They were all the ones listed in our cheat sheet. The Pythagorean identities, the reciprocal identities, the quotient identities, the sum difference identities, the addition subtraction identities, the double angles, the half angles, the reductions. Each one of these does something a little bit different. In section 5, all of that is an option. It is a method by which we could approach the problems we're going to be given. But the key difference is that much of section 5 is actually an algebra problem. It's an algebra problem with a trig equation thrown in. Here's what I mean. Table number 4. This is an even homework problem. You'll notice that there's not a lot to this problem. There's not some proof to do. There's not some fancy rewrite we're supposed to take into account. Instead, we're just asked to find all solutions. Now, that phrase will appear throughout the homework, and there's a secondary phrase we'll talk about afterwards that actually is the easier version. Find all solutions. What this implies is that you're going to solve this problem algebraically, with a goal in these problems to be as follows. Isolate the trig functions. Think of a trig function like a variable. So this problem on the board, one of the most common tricks to it is to approach it like it's an algebra problem. In other words, I have 2 times something equal to another number. For these problems, we will use the unit circle quite a bit, so make sure you have that available to you today. And the secondary thing will be, there will be multiple solutions for every problem tonight. Because for many of them that we're talking about, they're going to say find all solutions. There's a subtype in your homework, which is another type, where they ask to find just the ones that are on the unit circle itself. So, here we go. There are 4 steps I recommend for doing these kind of problems. They're as follows. Step 1, look for an algebra property. What do I mean by that? Well, that's very vague. Look for an algebra property. Things that you can add to both sides, subtract both sides, multiply both sides, divide both sides. Look for things you can use like factoring, distributing, completing the square, combining fractions, anything algebra in nature, much of which we've done in the last couple weeks in the other sections. All of those are fair game. Also look for things you can do trigonometrically by considering a substitution. Step 2, rewrite your problem using a substitution. Take the problem, rewrite it using one of the properties. Use the double angle formula, use the half angle formula, use the Pythagorean, use some other way to write this. Step 3, if those 2 steps are not very good, perhaps you just need to solve it algebraically, meaning that my goal becomes to rewrite this function as an algebra problem and then solve it. And then finally, step 4, check for extra solutions. Because these functions are cyclic, they tend to have duplicate solutions around a ring. We will talk about how each of those can be found and the proper way to write them. Let's start by looking at problem number 4. We are going to find all solutions. How we do that is simple. My main goal, isolate the trig function. So for this problem, I want to find some way to isolate, in this case, my sine function. When I say isolate, it's algebra in nature. Get the variable by itself. Whatever steps are necessary. Add, subtract, multiply, divide, factor, distribute, perfect, square, combine. Anything algebraic in nature, but I want sine by itself. Because if I can get sine by itself, I can apply other properties to get solutions. So, take this problem.
Divide by 2
Yeah.
is the answer.
Divide by 2 on both sides. So in this case, I'm using something traditionally algebra. Okay? So I get sine by itself. It is isolated. And I get square root 2 over 2. From here, once we've got it isolated, we want to try to use the unit circle to find the solutions. In this case, the unit circle will tell us 2 solutions. But the problem doesn't say find 2 solutions. It says find all. So let's go ahead and do the unit circle part. So at this point in time, I've isolated the function. And now, I'm using the unit circle. So, go to the unit circle. The sine function, as a reminder, represents the y values. So we go to the unit circle. Where will sine of theta equal square root 2 over 2?
135.
135 and 45.
Do you need like the radians?
For this section, almost everything will be done in radians. So,
Okay,
to give the two answers.
3 pi over 4.
So pi over 4 is 1, and 3 pi over 4 is another.
So you just radians will work.
Yep. So, do note, we want the radian answers. It's kind of obvious in the homework because of how they phrase the question. They'll actually say, make sure your answer is between 0 and 2 pi. That should be a key indicator that you're doing it in radians. Now, this is the correct solution if the problem says, find solutions between 0 and 2 pi. This is the correct answer. About half your homework problems are this way, where they say, hey, just focus on the unit circle ones. Don't worry about anything past that, which is nice, because those are the easiest ones. You just look at the unit circle, find them, you're done. However, there's a secondary part. If I am requested to find all solutions, it is important to remember that all these trig functions repeat on a cycle. We refer to that cycle as the period. So down here below, the only other thing I want to add to my notes is a reminder about how these functions act in terms of their cycle. Sine and cosine repeat differently than tangent does. In this case, sine and cosine repeat every 2 pi. So every 2 pi, it completes a new cycle, meaning it repeats new values that have the same solutions. In this case, we refer to that as 2 pi times k. Welcome to higher level mathematics. K represents the fact that this is going to repeat multiple times. How many times? Yes. As many times as you want it to. As many times as you need it to. That K tells you it repeats both positive times and negative times. In this case, K is the stand-in for every possible repetition of this cycle. For tangent, since it repeats every pi, it is written as pi k, because it repeats every pi cycles. It's a small difference, but one that's bigger whenever you look at the big picture. So, if I want to find all possible solutions, what I need to do is indicate that there are more answers beyond the 2 we have. We currently have out of 2 solutions pointed out on the unit circle. Thank you, Gary. Of pi over 4 and 3 pi over 4. Those are my 2 solutions that are on the unit circle. So where are the others? Well, here's how you write them. We write the first solution, pi over 4. And we tell it, hey, this is going to repeat. So I say plus however many times it repeats. So in this case, 2 pi k. This represents all possible solutions, because every 2 pi, I get another answer. So I write 2 pi k, indicating that every 2 pi, there is going to be a new answer. So pi over 4 is an answer. But pi over 4 plus 2 pi is an answer. Pi over 4 plus 4 pi is an answer. Pi over 4 plus 6 pi is an answer. Pi over 4 plus 8 pi is an answer. It will repeat. And because k is undefined, it also works in the negatives. So if I subtract 2 pi, I will get another answer. If I subtract 4 pi, I will get another answer. But 3 pi over 4 does the same thing.
And those are your 2 answers. Those are probably.
That's right. This represents all possible solutions. So in your homework tonight, there will be 2 types of questions. There'll be questions that ask about just between the unit circle values of 0 and 2 pi, and others that ask you to find all of them. How do you find all of them? Well, you have to use a little mathematical trick. Your alternative, if you don't like this mathematical trick, is to list every possible answer. I'll give you a hint. There's infinitely many of them, because you can keep adding 2 pi to find another one. So you start listing them, and when you die, you won't be done, so you'll fail. Make sure you write correctly. So the mathematical part of this, you might notice so far, is relatively simple. Getting the equation by itself, that's not so bad. Using the unit circle, that's not so bad. Writing your solution properly in the correct context, that's what makes it difficult. Because you have to understand that these are not the only answers. Pi over 4 is an answer, but so is 9 pi. 2 pi around that circle. So it would be 17 pi over 4, another 2 pi around that circle. Negative 7 pi over 4, another possible answer. Because anything being added or subtracting 2 pi is a possible answer. For this problem, my two solutions. If the problem says only in the unit circle, that's the easy ones. Just look in the unit circle, find the values. If the problem wants you to go farther, here's how we go farther. So make sure you're reading your problems, because there are a big difference between them. Most of the ones at the beginning are the ones where it's just between 0 and 2 pi. So note that. Do that. Concept, straightforward. We're going to algebraically solve an equation, use the unit circle to find our answers, and then adjust the answers based on whether we are doing it from 0 to 2 pi or all possible answers. Here we go again. So number 6. Very similar problem. Very similar.
Can I look for my wallet?
Number 6. This time, find all solutions. So our goal becomes first find the ones between 0 and 2 pi, then find the ones that are around those values by using the plus 2 pi k or plus pi k depending on the problem. If it's a tangent problem, we approach it a little bit different. So make sure you're reading your problems. Let's take a look. Number 6. We have 2 cosine of theta equals 1. Find all the solutions. So, your textbooks describe an interesting step that some of you guys may really like, because if you struggle with the trig functions, it can be really weird. What they say is, think of the trig function like a variable. So don't look at this as 2 cosine of theta equals 1. Look at it as 2x equals 1. Then you can solve it like a regular algebra equation from algebra 1. Just divide both sides by 2. You get x equals 1/2. And then you just plug the trig equation back in. So I'd use x as cosine. So you get cosine equals 1/2. Personally, I'm not a huge fan of this technique. Mainly because you're doubling the number of steps when it should be obvious from the beginning what it was. Now, the more complicated the problem gets, the more I will tend to do it this way. Because the more complicated it is, the harder it is to see the patterns with the trig function involved, when it's much easier when it's just a regular function. This will come up a lot when we look at the ones that involve quadratics, because there will be quadratic functions that have trig functions inside of them. So I take my function, 2 cosine of theta is equal to 1. I divide that by 2, getting cosine of theta equal to 1/2. I use the unit circle to determine my possible solutions. Where will cosine of theta equal to 1/2? Pi over 3. And 5 pi over 3. 5 pi over 3. Thank you, Madeline. These are the solutions between 0 and 2 pi. If the problem says look for the one between 0 and 2 pi, I am done. If the problem says find all solutions, I have to take one extra step. The extra step is clarify that there are additional solutions by a set pattern. Here we go. This is a cosine function. The cosine is modified by 2 pi k. In this case, my first solution is pi over 3, but to find the duplicate solutions, I would add 2 pi k. Because there are additional solutions every 2 pi. How do I write that? 2 pi k. Other textbooks, if you go to a college that does trigonometry and you take a class again for some reason, they sometimes use n for the same reason. K could be any integer value, meaning I could add 2 pi to get my answer, or I could add 4 pi to get my answer, or I could add 6 pi to get a new answer, or 8 pi, or 10 pi, or 12 pi, but it has to be some kind of 2 pi to get a new answer. The 5 pi over 3, same thing. Again, it's a cosine function. So these become my two solutions. Remember, these come from the unit circle. We find these two solutions from the unit circle. This piece is modifying from the cycle. Every 2 pi, this thing repeats. So I write 2 pi k, and you guys can repeat every 2 pi, however many times I want it to repeat. So the part in black is the actual solution. The red and blue are just to explain where each part came from. First part came from the unit circle. The second part came from modifying it by the trig functions cycle. Okay. So far, little easy ones. We'll try those out. Number 12. Number 12. Here we go. Number 12 says cosecant squared of x equals 4. Oh, that's number 12. Sorry. Cosecant squared of x minus 4 equals 0.
So the IC mean is the Pythagorean identity, or is that?
So that's a possibility now, right? Because it's cosecant squared, right? I have the option to rewrite using the trig identity. Okay? That is possible. So, you have every possible trig identity we talked about available to you now. How you choose to solve this problem is a mixture of how good are you at the algebra and how quickly can you see a trig way. Now, the same general rule is going to apply. You want to isolate some kind of trig function. You'll notice that I've given you the boundaries for sine, cosine, and tangent because, as you remember from last week and from previous sections, if all else fails, one of the best ways to approach these problems is with sines and cosines. Why? Because those are the ones on the unit circle. That is the other half of that problem. And so it is best, if possible, to convert it into sines and cosines and work from there. Otherwise, all the other trig functions are available to you. So, how are we going to approach the problem?
Add 4 and then get rid of the square root if you want.
Okay, I like the idea. Okay, so we're going to add 4 to both sides, so we're solving it algebraically. You can think of this like an x being squared. So we have x squared minus 4 equals 0. To solve for x, you would add 4 to both sides, then take a square root of both sides. The difference is, it's got a trig function involved. That does not change how the rules work, just makes you work a little differently. So we got cosecant squared of x is equal to 4, and then you said take a square root. So we're going to take a square root of both sides. Now, don't forget, from algebra, I get a plus or minus. Now this right here is really kind of a pain to do because we're not as comfortable with cosecants. So let's switch it into a sine. Cosecant, as a reminder, is 1 over sine. How does that help us? Well, if I can get the sine by itself, then I can use the unit circle to find my answers. But that's a big if. Can I get sine by itself?
You just multiply it over and then divide the plus minus 2 and get 1/2.
Very nice. So I'm going to multiply both sides by sine. And then divide. So I get 1 equals plus or minus 2 sine of x. And then he says divide. Okay, that's good. So I divide both sides by the plus or minus 2. And if you haven't done this before, like you can divide by a plus minus, same as anything else. Just make sure it stays consistent throughout. So you end up with the following equation. 1 over plus or minus 2 equals sine of x. Now at this point, don't forget algebraically, a plus minus just means you're going to do the problem twice. Once with a positive number and 1's for the negative numbers. So at this point, I'm going to do an algebra step. I'm going to take that plus minus and split this into two problems now. I'm going to have positive 1/2 equals sine of x, and I'm going to have negative 1/2 equals sine of x. I can do that because of the plus minus. The plus minus splits the problem. This comes from algebra 1. So the problem once for the positive 2, one for the negative 2, and both of these are on the unit circle. Which turns out we actually get 4 solutions for this problem. And that's fine. We're supposed to. And with the plus and minus of the case, we actually end up with more than 4. A lot more than 4. Let's do it. From the first piece, when does the sine function equal to 1/2? 5 or 6 is one of them. Any other places? 5, 5 or 6 is another one. Now, the negative 1/2, 7, 5 or 6. And what did you say?
11.
Okay. Now, if it asks for the unit circle values, these 4 are my answers. How does it ask for unit circle values? It will say between 0 and 2 pi. Some of your homework problems are written that way, so pay attention to them. If it says find all solutions, I have an extra step now that I've gotten these 4 answers. I want to showcase that there are more of them. Every cycle repeats. So what I'll do, plus, this solution is plus 2 pi k. This solution is plus 2 pi k. This solution, plus 2 pi k.
So for this tangent, which is plus pi k.
Yes, and in general, I don't like these 2 rules. You'll see tomorrow I make a modification to them. What I will do, instead of writing 2 pi, is I'll write the period. Because one way to make these problems more interesting is to change the period. In fact, let's look at our next one. This will be one where the period is different. And because the period is different, what we finish the problem with will be different. But are there any questions so far? We're algebraically solving a trigonometric equation. We use a unit circle to find the individual values, and if we need to find more values, we add in the period. The reason I also like using this version, period k, is because it's the same for both of them, which means I only have to memorize one equation. As long as I remember the period for sine is one thing and the period for cosine is something else. Okay, here we go. Next one. What if the period isn't 2 pi? What if it is something else? What if the equation had been modified a little bit more? This is problem like number 18. Here we go. 18. 18's instructions are a little bit different. It says solve exactly. Solve for all values between 0 and 2 pi. So I won't have to do the plus or minus piece specifically, but I should make sure I do find every possible value. Here we go. The equation number 18 will look a little bit different, and this is a red flag that you need to be considering this alternative form. Because the equation looks like this. 2 sine 2 theta equals 1. From way back in chapter 8 when we talked about graphing, that 2 on the inside is going to affect the period. The 2 on the inside will affect the period. It will change how the values repeat. That is important. I will show you my trick. I will show you the book's way. And I will show you kind of a common sense approach. All of which are very similar and will find the solution if you try them out. Here we go. First of all, The rest of it is pretty straightforward. I'm going to start this problem by getting the trig function by itself, dividing both sides by 2. So let's take that step. I divide both sides by 2. Woo! Divide by 2. I get sine of 2 theta is equal to 1/2. Now I go to my unit circle. My unit circle will find me the values for sine of theta, not sine of 2 theta. So my approach is to ignore the 2 theta until the end. Here's how. First, where is the sine function equal to 1/2?
Pi over 6 and 5 times.
Pi over 6 and 5 pi over 6. Now these are places where sine of theta works. So this is sine of 2 theta. So my technique is we take the inner piece and equal it to each value. Because remember, sine of just theta, okay, gives me those two answers. So to find the new answers, I use the modification of letting the new answers equal the angle in question. Yes, sir. That's not what happens. How do I get theta by itself? So to get theta by itself, I have to divide both sides by 2. So what do I get as my answers? What I get for the first one, theta is equal to pi over 12. And for the second one, theta is equal to 5 pi over 12. So the book says, well, don't you see a pattern? Like, what did we end up doing to get to our answer? Well, we divided everything by 2. So it says, why don't we divide by the coefficient every single time? It says, take our answers and always just divide by this number. To me, that's the same thing. It's just kind of a nice way of explaining what we're doing and why. But there's more things on the inside that can get kind of confusing. So what I will always do is I will take the inside and make it equal whatever we got from the unit circle and then take an extra step to solve it. Now, these are 2 solutions, but this thing repeats every pi period. The reason I bring it up now is because these are not the only solutions. I add to this. Now we're dealing with the sine function, but we're dealing with sine of 2 theta. That 2 affects the period. As a reminder, from back in chapter 8, how we determine the period for sine and cosine is we take 2 pi over n, where n is that number in front. So in this case, my period would be pi. Take a second. Remind us from chapter 8. The period in this case would be pi. So to find our values, we take pi. John, can you go with your word? We take the pi over 12. We take the 5 pi over 12. We add to it the period. So in this case, that would be pi k and pi k.
Best teacher.
Why pi k? Because it's the period times k. The period for this specific function is pi. The sine period is 2 pi, but sine of 2 theta affects the period of the sine function. So we want to always add the period to the problem. Again, this part is where we start to pull in pieces from other sections and other chapters. We want to always add the period to the problem. For sine and cosine, 2 pi over n will generate the period. For tangent, pi over n will generate the period. So there's a number up front. We can find the period very easily. Now, how do I determine which values are the right answers? Because this gives me all of the answers, right? We have pi over 12 plus pi k. We have 5 pi over 12 plus pi k. That gives me every possible answer. But I only really want the answers that are between 0 and 2 pi. Let's go over here for a second. I want just these. Now, obviously, pi over 12 is in that list. Because pi over 12 is between 0 and 2 pi. So is 5 pi over 12. It is also in the first quadrant. But it turns out that plus pi k gives a bunch of other answers, and some of those answers are also in the first 2 pi. So the last step I would tell you, use the plus pi k to make a list of all possible answers. Don't literally make a list of all answers. Go far enough to see which ones are ending up in here. Take a look. I'm going to use some space over here. As just going down below on your paper. You need to get your space. I'm going to do. Then I'll make a list. What are my possible answers? From the first one. Well, 5 or 12. That's a possible answer. I have more possible answers. I could do pi over 12 plus pi over 12 plus 2 pi over 12 plus 3 pi. All 4 of these are possible answers. And there's more. But at some point in time, you're going to exit the boundaries of the problem. The problem said, hey, focus on the ones that are just between 0 and 2 pi. Well, it turns out 2 of these fit that match. Pi over 12 fits in that. Pi over 12 is between 0 and 2 pi. But one of the other ones is too. This one. These 2 are in this range. Now there are more answers, right? Because I can just add another pi. Then I get pi over 12 plus 2 pi. I got another pi. Pi over 12 plus 2 pi. Pi over 12 plus 4 pi. Pi over 12 plus 5 pi. Pi over 12 plus 6 pi. I can also subtract some, right? Pi over 12 minus pi. Pi over 12 minus 2 pi. Pi over 12 minus 3 pi. Pi over 12 minus 4 pi. But I'm only focusing upon the ones that are in here. This listing. If they're not in that listing, I can't use them. So yeah, there's more answers, but not where I want. So there's 2 answers. Pi over 12 and pi over 12 plus pi, also known as 13 pi over 12. Simplified. The back of your book will simplify them. 13 pi over 12. The bottom ones? 5 pi over 12 is one answer. There are more. How many more? Well, let's check on making a list, and then only keep the ones we want from the list. So, some possible answers. 5 pi over 12. We could also do 5 pi over 12 plus pi. 5 pi over 12 plus 2 pi. 5 pi over 12 plus 3 pi. And I could keep going. I could do 4 pi. I could do 5 pi. I could do 6 pi. But what you want to do is you want to stop once you reach the boundary. My goal is to stay between 0 and 2 pi. Some of these are in there. Some of these are not. Let's make sure to grab one of the ones we need. 5 pi over 12, that's obviously in the answers. But so is 5 pi over 12 plus pi. This would be 17 pi over 12. This problem had 4 solutions. Despite the unit circle only giving us 2. That's an important note to make here. The unit circle told us these 2 solutions, which we modified using the period. But those 2 were not the only ones. Because of the period, we ended up with more. If you see a period change in the problem, it indicates there's more work to do. That's the big thing I'm going to tell you. The period change means there's going to have to check every aspect has changed now. Because the period is different, everything else changes. When we talked about graphing them, that was a constant theme. Changing the period changed a lot of stuff. Well, that doesn't mean we have to solve for them too. Let's do one like this. We'll call it a day. I'll post the first part of the homework assignment. Let's do one like, number 22. This one's fun. 22. Again, find all solutions between 0 and 2 pi. 2. Cosine of 5 or pi over 5. Equals square root of 3. Again, we're looking for all possible ones between 0 and 2 pi per the instructions. All right, let's do it. First, the easiest pieces are algebraic solving. How am I going to get the cosine function by itself? By 2, easy. So I get the following. The cosine function of pi over 5 theta equals square root of 3 over 2. Now, the unit circle will solve for the base ones. We can then manually solve for the right ones using the period. So I'm going to write 5 pi theta equals pi over 5 theta equals, from the unit circle, where does the cosine function equal square root of 3 over 2? Pi over 6. What was the other one? 11 pi over 6, yeah. Okay, well, let's find our two solutions. So if I divide by pi over 5, calculator can be your friend here. If I divide by pi over 5, I end up with the following. In division, I would use KFC. The pi's end up canceling. You end up with 5 over 6. Double check me in case I'm wrong.
Is the next one like 55?
Nope.
Not 8,
Either two. I'm
Well,
not
I was
doing
saying 30, but it's not 30.
So, these are my possible solutions. But remember, these possible solutions are going to be modified by the period. So, I'm going to add to each of these possible solutions. Well, I want to add by the period times k. For this one, since we're dealing with cosine, that'd be 2 pi over n, so 2 pi over pi 5. So that becomes actually, as weird as it sounds, 10. If you check and plug in pi over 5 into this formula, 2 pi over pi over 5, the pi's cancel, the over 5 uses KFC, we get 10k. So we get 5 over 6 plus 10k, we get 55 over 6 plus 10k. This is not 10,000, this is 10 times k. Now, what I want to check now is, are any of these, or all of these, or some of these in the section I want between 0 and 2 pi? Well, let's make a list. So, possible answers. Okay, so I'm going to make my double list. 5 over 6 is 1. I also have 5 over 6 plus 10, 5 over 6 plus 20. And don't forget, you can also do subtraction. 5 over 6 minus 10, 5 over 6 minus 20. So those are all possible answers, but only some of them are in my range. On the second list, 55 over 6. We'd also have 55 over 6 plus 10, 55 over 6 minus 10, plus 20. I'll keep the same formula. 55 over 6 minus 10, 55 over 6 minus 20. Remember, I am stuck in this range. Now, I need to figure out if any of these are actually in the range. To do so, I'm going to do it in two ways. One, I'm going to convert my range into decimal form to make it easy to compare these numbers to. And I'm going to convert all of my answers into decimal form. If you've got a calculator, I'm going to ask for your help because you're going to want to do it on your problem as well.
I need
Here we go.
Cody Owens, Jason Metcalf, Tristan Stone, Michaela Irwin, City Office.
0 is obviously 0.
Jason Metcalf, Cody Owens.
2 pi, 2 times 3.14 would be 6.28. So this is the range I'm supposed to stay in. 5 over 6 is 0.83 repeating. If I add 10 to that, that becomes 10.83 repeating. If I add 20 to that, that becomes 20.83 repeating. 5 over 6 minus 10 would be negative 9.16 repeating. 5 over 6 minus 20 would be negative 19.16. Repeating. So as you can see, in this list, only one of those 5 values is actually in my solution set. The first one. If you add 10, it's too big. Add 20, too big. Subtract 10, too small. Subtract 20, too small. The nice thing is once you've found your barrier, none of the ones past are going to work. Okay? So go as far as you need to. All right, let's take these other ones. 55 over 6. I cannot do that one in my head very easily. 9 point something? Okay.
9.3.
9.3?
I'm guessing.
55 over 6. Okay. I must. I think you're right.
9.16.
9.16? Now, you might notice 9.16 is too big, meaning this can't be an answer. Adding 10 to it is going to also be too big. Too big. Subtracting 10, subtracting 10 gives us negative 0.83 repeating, which is, you'll notice, again, between 0 and 2 pi, between 0 and 6.28, that's too small. So it turns out with this problem, there's only one answer. But we only know that by checking the other answers and seeing are they in my range or not in my range. So again, if the problem says find all solutions, we've done that right here. That is this piece right here. If the problem says find those in the range, we have to make sure to isolate only those that are in the range. In this case, 1, 5 over 6. We'll look through some more examples tomorrow. Oh, yes. So I use the formula over here, which is 2 pi divided by whatever my coefficient is. That would be 2 pi over 5. And I turn this into 2 pi over 1. Use KFC, so 2 pi over 1 times 5 over pi. Oh my God. Did I simplify that wrong?
No, you didn't.
Okay, good. I was worried for a second there. Okay. From here, the pi's cancel. 2 times 5 gave us a 10. That's where we got the 10 and the 10 came from. I just did it really fast. I'm sorry. I'll make sure tomorrow to go fast that every time.
I didn't know if it was supposed to go 2 on the bottom or pi with 5 on the bottom.
Pi over 5. That was our bell. Enjoy your lunch. Or your next walk, whatever you're doing.